Yes, thank you, Professor Shufalian. Thank you very kind introduction to me. So I'm going to start my talk today. Can you see my screen?
Yes, I can see it.
Yep. Yeah, thank you very much. And today, thank you for giving my great opportunity to give a talk on the IMRR UNESCO Chair web seminar. So my name is Mori from Kyoto University, Yokohama National University, Swansea University, and Swansea University. And today I'm going to talk about climate change impact on the mainly coastal extremes, especially extreme natural hazard. So Europe doesn't have this influence, but typhoon is quite important in East Asia, and this is the most severe and extreme event in Asia and the Pacific region. So, for example, Typhoon Haiyan struck to Philippines in 2013, and that gave 6,000 casualties in Philippines, and then Typhoon Winston struck on the cyclone Winston struck on Pacific Island, and then it also gave a devastating damage in Pacific Island around Fiji. And then Typhoon Jebi 2018 struck on Japan, and then which gave over 10 million US dollars damage, including inundation of the Kansai airport that you are looking now. So typhoon is pretty important. And then we expect a severe typhoon is getting increased in the future due to the climate change. So we want to quantify the hazard, especially river flooding and the coastal flooding. And then to understanding the hazard risk, we need to estimate our project hazard frequency and intensity. That is the main topic today. And additionally, we have to think about long-term changes in vulnerability and the society changes, especially economics and the population changes are pretty important to understand the risk. Then if we are focused on the coastal risk, we also need to consider the several natural phenomena, including sea level rise, coastal flooding, and so on. So, and then river flooding and the water resources or heat wave are also important to understand the potential risk due to the climate change. Then in Japan, we have 5 years national climate research program funded by Ministry of Science and Education, so-called MEX. So now we are fifth phase of the national climate research program, so-called Sentan program, started from 2022 to the 26. Then we have 4 groups from theme 1 to theme 4. And first 3 groups are mainly global projection and then regional projections, led by Atmospheric Ocean Research Institute of University of Tokyo, JAMSTEC, and Meteorological Research Institute in JMA in Japan. And then I'm PI of the theme 4, which mainly focus on extremes and hazard, considering climate change. So based on this Sentan program, we want to estimate future extreme and hazard based on our theme 4. And then we have basically 3 groups for understanding physical processes and future impact, started from the integrated hazard model group and the hazard mechanism and the hazard event attribution and so on. So today I don't have enough time to explain in detail, but basically what we are working on now is try to project long-term changes in natural hazard in Japan or East Asia scale from global projection, regional downscaling to the hazard assessment. That we are working on this Sentan program now. Then understanding global to the local climate risk is also important because they are connected. Because even if we want to understand river and the coastal flooding risk in local level, we have to understand the relation between global scale to the regional scale. And then we also need to include all the other phenomena from typhoon, tropical cyclone, and the sea level rise, and so on. So, and then it is also important to understand relation between climate change, that is a long-term trend, with natural variability. Natural variability here means El Nino, La Nina type large-scale variability, and other teleconnection effect. So topic is pretty broad, and then we need many knowledges from climatologists to the engineers. So this is what we are working on in Japan, over 400 people together from Thema 1 to the Thema 4 now. Then in our project, we have 3 goals. One is developing integrated hazard model, which under the development now, so I don't have enough time to explain, but we mainly focus on the hazard to the risk assessment now. And then we are also making climate risk information for the central government or public now. Then we expect we may publish many papers for IPCC next report, assessment, 7th assessment report, and the related special report now. And we also want to contribute to the Japan's national report, and making data set for scientists, engineer, and public. And we are also collaborate with governmental agencies and the technical users now. Then starting point is a global projection and the regional downscaling. So what we have been working on this part is making large ensemble projection. In Japan, we develop a large ensemble projection, so-called D4PDF. Here, it's acronym, but anyway, this ensemble projections that globally 60 resolution over the globe, and then it downscale to the East Asian scale. This region with 20 horizontally 20 kilometer resolution over the East Asia, and we also have one more downscale to Japan with 5 kilometer resolution over the Japan region. And then this ensemble is pretty unique because one ensemble consists of the 6 years simulation. Then we repeat 6 years global to the region simulation times 100 times in historical climate now, present climate. And then we also repeat 90 times of 60 years ensemble for 2-degree warmer climate and 4-degree warmer climate. And then we also conducted additional 100 ensemble for non-global warming condition too. So then based on this, we can estimate future changes in mean and extremes for non-global warming condition, present condition, and the future warmer condition together. Then both different climate conditions, we have over 5,000 years. So this is pretty useful for understanding and the extreme of the understanding and the extremes, because conventional climate projection in the order of the less than 100 years, I would say 20 to 50 years. But if we have few thousand years projections, it is easy to estimate 1 by 100 or 1 by 200 years extreme, because it's an interpolation. So that this kind of longer record cannot be obtained by the observation data set. Then this is just animation of the meaning of the ensemble. So wait a moment. Yep. So we just repeat 60 years simulation in historical and warmer climate. Then this kind of global climate simulation is equivalent to the kind of weather forecast. So we just repeat different, slightly different part of the condition with global model to the regional downscaling model. So based on this, we can estimate precipitation, wind, pressure, and so on. Then now you will see, and then if we can downscale into the 5-kilometer grid, we will see more realistic cloud patterns and typhoon and so on. So downscaling is also necessary to understand regional or local risk. Then large ensemble can reduce uncertainty. This is one example how future changes in one-day precipitation can be different depending on the number of the ensemble. Now horizontal bar indicate the number of ensembles. So 1 indicate 60 years and 90 indicate 5,400 years. Then blue, a different color indicate this different percentile. So if we focusing on the 95 percentile of the daily precipitation changes, this is maybe in Tokyo, then if we have fewer ensemble, uncertainty range in the future change has a large, maybe 30 to 40% compared with average. But if as number of the ensemble increases, this kind of uncertainty can be dramatically reduced. So based on large ensemble projection, we can more statistically easily to obtain stable extremes. Then this is just an example of the 100 years flat map in Japan. So again, we use D4PD 5-kilometer Japan downscaling data set with RRI model developed by Professor Sayama at Kyoto University. So this model solved all the rivers entire Japan. Then left is a present climate, and the middle is a 2-degree, and then right is a 4-degree warmer climate, and the different color indicate increased ratio of the 1 by 100 years flat compared with present. So present is a baseline. So a different color indicate a different amplification of the 100 years flat level in different conditions. So based on this, we can estimate future changes in extreme flat level entire Japan now. Then this is another example how tropical cyclone can be projected based on this large ensemble. So wait a moment. Oops, oh, sorry. Oh, it's gone. Yeah, based on this left hand indicate 60 years one ensemble run, and then around Tokyo area. So one line indicate one typhoon passing. So we have only 4 to 5 important typhoon around Tokyo Bay. Center of the figure indicate the Tokyo Bay. So even if we have 60 years climate run, we have only few events around Tokyo Bay. That is not significant for extreme storm surge analysis. But if we have 100 more, we have enough number of the ensemble, we have enough number of the members, so we can estimate extreme storm surge around Tokyo Bay or a particular area. So Tokyo is just an example. So large ensemble can analyze extreme at a particular area. So this has been very significant progress last 5 to 6 years in Japan. Then I'm moving on the more physical understanding of the future changes in typhoon. So left-hand panel indicate future changes in the number of the cyclone per year in Western North Pacific area. Western North Pacific area, and blue indicate present climate. Red color indicate plus 4K warmer climate, and then black line indicate the observation by satellite. Then shade indicate confidential level. Then based on this, present climate simulation pretty matched with observation, blue and black. Then in current, we have 26 to 28 typhoons per year at the western North Pacific region. Then on the other hand, if future 4-degree warming condition is achieved, then a number of the typhoon will be reduced to the half. So typhoon, we will see less typhoon in the future in warmer climate. On the other hand, right-hand panel indicate central pressure, minimum central pressure of the typhoon at typhoon I. Then color are also same to the left panels. So in present climate, blue line, occurrence probability of the typhoon stronger than 90-20 hectopascal, it's pretty strong, can be appeared every 2 or 3 every 1,000 typhoon. But on the other hand, for such kind of intense strong typhoon can be occurred 2 or 3 of every 200 typhoon. So the typhoon occurrence probability of such intense typhoon can be 10 times more in the 4-degree warmer climate. So so we will see fewer typhoon, but we will see intensified, stronger typhoon in the future. That's our projected future based on Japan's model now. Then such kind of future changes are not uniform in the region. So now we are focused on the western North Pacific region. Sorry, I'm excluding Atlantic region, but in horizontal axis indicate the maximum intensity of the tropical cyclone. So 0 is a 0 hectopascal, and minus means a stronger tropical cyclone in the hectopascal. And the vertical axis indicate the latitude. So 10 to 15 correspond to Philippines, and Japan, middle of China, Korea is above the 30 degree in north. So different color indicate a different global emission scenario. So for example, RCP 8.5 correspond to the 4-degree warmer climate. And then in this case, typhoon will be stable or slightly weaker. Plus means a weaker typhoon in the future. Then, but however, it goes to the negative to the north. So it means typhoon will be stronger to the northward. So higher emission scenario, we expect more than 10 to the 15 hectopascal stronger tropical cyclone in the future. However, right-hand panel indicate the future changes in sea surface temperature, SST, with same color. So future SST, sea surface temperature, will be linearly warmer from south to the north, but the tropical cyclone intensity shows a non-linear curve like this. So SST is one of the key factors to understand tropical cyclone intensity, but not all. So understanding future changes in tropical cyclone is more complex compared with SST. Then if we are focused on the mid-latitude, around 30 degree in north, where we expect most active changes in the future in this range. Here's Shanghai, and then Korea and Japan. Then now horizontal axis indicate the months from January to the December, and vertical axis indicate the future changes in the tropical cyclone intensity. So again, negative means the stronger in the future. So we will see most severe changes in August to November until October in the future, and different emission scenario shows a different pattern, but overall, all the emission scenario indicate future changes in a negative, it means a stronger typhoon in summertime of Western North Pacific. So this is our current understanding on the tropical cyclone. And then we are now moving to the total water level or extreme sea level, because this is pretty important for understanding coastal hazard risk with climate change. So overall, here is the mean sea level, which is a very gradual mild change of the sea level. And then we expect sea level will be rise in the future up to 40 centimeter in by a 2-degree climate, warmer climate, and 80 centimeter in 4-degree warmer climate at the end of the century. And then additionally, we have astronomical tide that will not be changed by the climate change. But in addition to the mean sea level change, we will see future changes in the storm surge and the wave run-up zone. So adding all mean sea level change, sea level rise, indeed changes in storm surges and the wave run-up, we have to make assessment of the total water level. That is pretty important to understand coastal hazard risk in the future. Then first step is how we can estimate storm surges, and the one straightforward approach is running storm surge model entire the globe. So, but it's time consuming, and then it is also statistically unstable. So we propose maximum potential storm surge MPS framework a couple of years ago, which is a combination of the theory of the tropical cyclone maximum potential intensity theory proposed by Kerry Emanuel. And then we, based on maximum potential intensity of the tropical cyclone, we try to estimate maximum potential storm surge height based on the kind of several assumptions. I don't have enough time to explain, but we try to estimate, develop maximum potential storm surge height based on the semi-empirical theory. And then based on this, we try to estimate maximum storm surge. This is one example how maximum potential intensity of the tropical cyclone can represent tropical cyclone intensity in the model. So left-hand panel indicate modeled tropical cyclone by global model indicated by dot. So different color indicate different tropical cyclone intensity, and the background color indicate the maximum potential intensity from the monthly mean values. So if color is matched, MPI, maximum potential intensity theory, is worked pretty well. And overall, there's several biases, but above the 15 to 20 degree in north, it works pretty well. Then we try to estimate future changes in maximum tropical cyclone intensity and maximum storm surge intensity. So this is one of example how future maximum potential intensity of the tropical cyclone will be changed from present to the future, left panel. And then right-hand panel indicate the future maximum potential storm surge height from present to the future. Blue is the historical run, and the two different colors indicate different warmer climate condition, and orange indicate 4-degree warmer climate, and yellow indicate 2-degree warmer climate. So in 4-degree, both tropical cyclone intensity and the storm surge height can be almost linear from present to the future. But for 2-degree, it will be stabilized around 2050 or 2060, like this. So anyway, if tropical cyclone is intensified 5 to 10 hectopascal in here in Western North Pacific, storm surge will be increased 40 to maybe 1 meter in our theory in Osaka. Again, storm surge changes in storm surge are highly depend on the region of the interest, but this is one example. And then we try to expand our analysis in the East Asia region. So in Tainan, the southern part of Taiwan, there's no change of the storm surge potential maximum storm surge in here because tropical cyclone intensity will not be changed so much because it's too south. Then if we move to the move from Taiwan to the Shanghai, this one, we will see more linear increase of the potential storm surge from present to the future in here. And then if we move to the Incheon, western coast of the Korea, we will see more significant changes in maximum potential storm surge in this area. And then, yeah, it's actually pretty sensitive in latitude and the shape of the bay. So storm surge is a very small scale compared with typhoon. So results can be very different depending on the latitude and the shape of the bay. Then, oh, sorry, I'm going to skip it. Then this is a summary of the future changes in maximum potential storm surge in Osaka case as a function of the emission scenario. So RCP 2.6 corresponds to 2 degree and 8.5 corresponds to 4 degree. So in this case, we expect around a 60 centimeter increase at Osaka Bay, and which correspond 70 to 80% to the sea level rise. So sea level rise is a starting point, but we expect additional extreme sea level increases plus 70 to 80% by the storm surge. Then we are also working on the wave climate projection. So this is a activity supported by WMO. So the project is so-called CARCRIP, Coordinated Ocean Wave Climate Project. You can download most of the data from our website. So we try to make an ensemble coastal wave projection from global to the regional projection based on this CARCRIP project. Then this is our latest result for IPCC AR6 previous report. So this is future changes in mean wave height. Oh, sorry, it's something missing, but wave height. So top middle indicate significant wave height in present climate, and then bottom two indicate 2 degree and 4 degree warmer climate, and then future changes in mean significant wave height is significant in higher emission scenario because climate change signal is larger than natural variability. Then we found decreasing mean wave height in the mid-latitude of the Pacific Ocean significantly, as well as the Atlantic Ocean. So a mean will be decreased due to the greenhouse gas emission in northern hemisphere. But if we are focusing on the southern hemisphere, story is different. We will see increases in mean significant wave height more than half of the southern hemisphere. So in wave height, mean wave height changes are pretty different in the ocean scale, ocean basin scale. Then we also want to know the extremes. So this is our extreme wave projection result, and top left is a mean, and the bottom left is a 1 by 10 years extreme wave height. Then again, green is a positive, and oh, sorry, it's something wrong. Yeah, sorry. Left-hand panel indicate the 1 by 100 years wave height excluding typhoon effect, and then right-hand panel indicate 1 by 10 years wave height including tropical cyclone. Then if we include tropical cyclone, 1 by 10 years wave height will be significantly increased up to 3 to 4 meters in this region, because we will see, as I already explained, the future tropical cyclone intensity will be stronger in the northwestern Pacific region, in the especially mid-latitude. So based on that projection, we will see increases in the extreme wave height in Western North Pacific. This is a result. Then we also want to get similar result of the storm surge in the global scale, but it's under the development. Now we started new project, so-called SurgeMIP, based on the supported by the WMO, World Meteorological Organization. Now we started to make ensemble storm surge projection in the global scale. So it's just started. So you will see our result within 2 or 3 years. Then last part of my talk will be more application of our scientific results. In Japan, we have a national assessment report every 5 years. Now we just published physical science part of the Japan's national report in this year. Then, as I already explained, we have national climate change projection research every 5 years. So these are kind of couples, twins, research part and the national report kind of twins in Japan. And then based on this, Japan's national report support the resilience infrastructure development for natural hazard. So, for example, this is a new river flood control plan with climate change in Japan. This act was issued 2021, and then in this national river flood control plan, government used D4PDF, our large ensemble climate projection, and then based on this projection, projected future flood risk will be summarized like this. In rainfall intensity will be increased 10% to 10 to 50%, it depends on the region, in 2-degree scenario, and then flow rate will be increased 20% at 1/100 or 1/200 years return period flood, and then frequency of the flood will be double based on this projection. So this is not scientific result. This is the national policy now. Then a similar act has been issued for coastal protection. This is a new coastal protection plan with climate change in Japan. So since 2020, Japan government issued designing a coastal infrastructure considering sea level rise and increases in storm surges and waves based on our projection D4PDF plus IPCC report for sea level rise. So before that, this kind of projection was pure research, but now our research is highly connected with national policies now. Then this our projection or scientific projection is getting important for the adaptation, because this is one of schematic graph. Blue color indicates the hazard intensity. Hazard intensity can be regarded as water level in the river or sea level, water level in the ocean. Then green line indicate a capacity limit. It can be regarded as a height of the dike or embankment. Then even now, on the horizontal axis indicate the time from present to the future. Then red line indicate the trend of the global warming. In short, it can be correspond to the sea level rise or increases in precipitation. Then even now, present climate, some disaster has flooding can be occurred if water level exceeds capacity limit. But however, increases in some trend, intensity of the hazard will be increased like blue lines. Then we have to adapt with changing climate, right? Then adaptation, the time scale of the adaptation is important because we cannot rise the dike height one day. So we have to consider the time scale of the adaptation that indicate green dashed line. So if we have to increase the capacity before starting increases in the hazard intensity, generally speaking, because otherwise sometimes it becomes too late to increase the capacity limit if time scale of the adaptation takes so long. So we are working on now. So we have to combine time scale adaptation, risk assessment, so on. So we want to propose earlier and smart adaptation for particular region or particular target now. And this is one of example in Osaka. Sorry, there are so many Japanese in this figure, but this is city of Osaka. So blue color indicate low-lying area. In Osaka, more than 1.7 or 1.8 million people lives below the sea level, mean sea level. Especially red-colored area below the sea level. This is a very highly populated area. Then historically, several severe typhoon and storm surges attacked in this region. Then Osaka installed 3 storm surge barrier at the river mouth. Then it has been succeeded to protect storm surges propagation from the ocean side to the inland side. Then it works pretty well so far, but now after 60 years later, this current storm surge barrier need to be replaced by the aging, and then new construction started 4 years ago. Then we try to contribute our scientific data to design new storm surge barrier, including sea level rise and intensified typhoon and so on. So based on our projection, we decided new design, including sea level rise and increases storm surge and waves for this gate design. Then I have no time to explain detail, but based on cost and effectiveness, plus uncertainty in the future projection. So we split 2 parts for designing new gate with climate change. One is a gate and mechanics, which should be considered 2-degree warmer condition due to the governmental policy. 2 degrees of government policy in Japan. And then, but we try to keep some space to upgrade for much severe warmer climate condition for gate and mechanics, because especially mechanics are relatively easy to upgrade later. On the other hand, foundation, which is under the sea, it is pretty difficult to upgrade. So we considered much severe 4-degree warmer condition designing foundation, because it's pretty difficult to upgrade in the future. So we try to combine cost-effective and the safer design, including uncertainty of the future changes like this. Then this is just one example, and now we started to develop and implement different infrastructure designing in Japan. Then I would summarize a challenge of the infrastructure design considering climate change. Before including climate change, present design protocol of considering climate change, considering hazard, are more statistical estimation. For example, if we want to design the river dike embankment, we need to estimate 1 by 100 or 200 years event. That is kind of application of the extreme value analysis as a random process. succeeds. However, if we want to design such kind of critical infrastructure considering climate change, we have to consider several different uncertainties. One is the uncertainty of greenhouse gas emission scenario, because we don't know much about future warmer climate at this moment. It can be either 1 degree, 2 degrees, 2 degrees, 3 degrees, 4 degrees. So we have to consider the uncertainty of the greenhouse gas emission. Second is uncertainty by the climate projection itself. Even given greenhouse gas emission scenario, different climate model gives a different future phenomena intensity, like a tropical cyclone. So we have to consider the uncertainty of the future by different climate projections. Then time scale is also important, because future changes is time dependent. So if your critical infrastructure design ended 2050, we need to consider water level increase like this. But if your critical infrastructure life will be ended at the end of the century, future changes is double or triple like this. So we also need to consider the time scale due to the climate change. Then society will be changed, because risk is a combination of the hazard, vulnerability, and then society, right? So if population and asset will be changed, future risk will be changed without changing hazard. So society change must be also important to be considered. Then, we have to seriously consider the so-called adaptation pathways, including time scale of the adaptation. So now we are facing new challenge, designing critical infrastructure with climate change. Then in summary, just brief summary of my talk today. First, the coastal hazard or natural hazard will be severe due to the climate change. And then they are highly dependent on the region. And then East Asian scale tropical cyclone plays very important role. Then climate projection is also useful for engineering design, because observed data is pretty limited, up to 50 to 70 years, depend on the different target. However, we can increase such kind of time scale based on the climate simulation now. So of course we have to correct the bias, but climate projection is getting very useful for engineering design, especially critical infrastructures. So yep. Then this is the end of my talk. Thank you very much.